Yet we have studied about the properties of solids. The properties of solids are all due to the compact arrangement of the particle. The compact arrangement of the particles inside the solid can be studied by a concept called as close packing. This close packing can be studied by three different approaches. That means the close packing in one dimension, the close packing in two dimension, and the close packing in three dimension. Let us take one by one. So let us take the close packing in one dimension. What is the close packing in one dimension? If the particles of the solids are considered as the spheres. If the spheres are placed adjacent to one another in a row, then it is called as close packing in one dimension. So here all the particles are arranged in one dimension, therefore it is called as close packing in one dimension. Here the coordination number of close packing in one dimension is 2. Here coordination number means the number of nearest neighboring sphere to the given sphere, that is called as coordination number. So here if you consider it has the reference sphere, to this sphere there are two particles which are in contact to this sphere, therefore the coordination number of this arrangement is 2. Nextly, we shall move on to the close packing in two dimension. The close packing in two dimension are of two types, that is square close packing and hexagonal close packing. This type of packing is achieved when the row of spheres are placed one above the another. Then we will get these two types of close packing, which are called as two-dimensional close packing. Let us take first square close packing. Here square close packing means this type of packing is obtained when the spheres of a row are placed right above the spheres of the another row. Then we will get this kind of close packing, that which is called as a square close packing. Why we are calling it as square close packing means if you connect the centers of each sphere, we will get a perfect square. Therefore we are calling it as square close packing. Nextly we shall move on to the hexagonal close packing. Hexagonal close packing means this is achieved when the spheres of a row are placed right above the depression produced by spheres of the another row. So if you place the sphere of one row is placed on the depression produced by the spheres of the another row, then we will get the hexagonal close packing, because if you join the centers of each sphere, we will get a regular hexagon. Therefore it is called as hexagonal close packing. Now we shall study the close packing in three dimension. The close packing in three dimension can be achieved by placing the layers of two-dimensionally close packed particles or placing one above the another. So let us go for simple cubic structure here. If two or more than two square close packed layers are placed one above the another in such a way that the particles of one square close packed layers are placed right above the particles of another square close packed layer, then we will get a crystal system that is called as a simple cubic structure. This type of arrangement is called as AAA type of arrangement. Why? Because the same pattern of arrangement is repeated, therefore it is called as AAA type of arrangement. Yet we have studied three-dimensional close packing by using the square close pack layers. Now let us discuss three-dimensional close packing by using hexagonal close pack layers. If the spheres of hexagonal close packed layers are placed, depression produced by another spheres of another hexagonal closed pack layer, then we will get some empty spaces. They are called as voids. So voids can be defined as it is the empty space present between the spheres of solids or the particles of the solid is called as voids. When two hexagonal closed pack layers are placed one above the another, we will get two types of voids. Those voids are called as tetragonal voids and octahedral voids. That can be studied as if the sphere of one hexagonal layer is falls on the void produced by another layer, then the void form is called as tetrahedral void. So because here four spheres are present in this void, if you connect the centers of each sphere, we will get regular tetrahedral. Therefore, it is called as tetrahedral void. Now we shall move on to the octahedral voids. These octahedral voids are formed when a void of a layer falls on another void of a layer. That means if trigonal void of one hexagonal close packed layer falls on the trigonal void of another same type of layer, then we will get a void which is called as octahedral void. So if you connect the centers of each spheres at this void, we will get a regular octahedral. Therefore, it is called as octahedral voids. So, the number of tetrahedral voids formed will be the twice of the number of octahedral void formed. That means if n is the number of particles involved in the close packing, then the number of tetrahedral voids formed is equal to 2n. The number of octahedral void formed is equal to n. Now we shall discuss about hexagonal close packing in 3 dimension and cubic close packing in 3 dimension. Both the packings are achieved when three layers of hexagonal close packing in 2 dimension are placed one above the another. So if the tetrahedral void covered by the sphere of the third layer, if the tetrahedral void is covered by the spheres of the third layer, then the packing obtained is called as hexagonal close packing in 3 dimension. So that means if this trigonal void is covered by the particles of the second layer, then it is called as tetrahedral void. If this tetrahedral void is covered by the particle of the third layer, then this arrangement is called as hexagonal close packing. This type of arrangement is called as AB, AB, AB type of arrangement. So therefore it is called as hexagonal close packing. Now we shall move on to cubic close packing. Cubic close packing in 3 dimension. If the octahedral void is covered by the sphere of the third layer, then this type of arrangement is called as cubic close packing in 3 dimension. That means this octahedral void is formed by when two trigonal voids are placed one above the another, we will get one octahedral void. If this octahedral void is covered by the sphere of the third layer, then the crystal system formed is called as a cubic close packing in 3 dimension. This type of arrangement is called as ABC type of arrangement. That means all the 3 layers are in different format. That is ABC. Therefore, it is called as cubic close packing in 3 dimension. Now we shall discuss about crystal lattice or space lattice. Crystal lattice or space lattice is nothing but it is a 3 dimensional diagram which represents arrangement of particles of a solid. So this is called as space lattice or crystal lattice. And the points which represents, so you can observe here, it's a 3 dimensional diagram which represents the arrangement of constituent particles of a sodium chloride. This entire diagram is called as space lattice or crystal lattice. These points are called as lattice points. Lattice points means these are the points in the space which represents the particles of a crystal system, that is called as lattice points. Now let us go through the unit cell. Unit cell means the smallest repeating unit of a crystal system is called as a unit cell. If you take the entire crystal lattice of NaCl, it consists of the smallest repeating units. They are called as unit cells. There are 2 types of unit cells. They are primitive unit cells and non-primitive unit cells. Here, the primitive unit cells means if the particles of the unit cells are present at only the corner of the unit cell, then such a type of unit cells are called as a primitive unit cell. Next, non-primitive unit cell means there are 3 types of non-primitive unit cells. Here, the atoms or the particles are present at the corner as well as other parts of the unit cell. Such a kind of unit cells are called as non-primitive unit cell. There are 3 types of different types of non-primitive unit cells. One is body-centered cubic unit cell. Here, along with the corners of the particles, along with the corner particles, here particles present at center of the unit cell, face-centered cubic system, so are face-centered unit cell. In here, along with the corner particles, the particles are present at the center of each face. Such a unit cell is called as a face-centered unit cell. Nextly, we have end-centered unit cell. End-centered unit cell means here, along with the corner of the unit cell, the particles are present at the centers of the 2 opposite faces of that unit cell. That is called as end-centered unit cell or face-centered unit cell. Side-centered unit cell. We have studied the formation of a crystal system under the concept close packing. Now let us discuss how many crystal systems are possible to form and how many space lattice are possible. There are 7 basic crystal systems are possible and 14 different Bravais lattice or the space lattice can be formed. 7 basic crystal system, 14 space lattice. They are named after the scientist called as Bravais because he has discovered those all crystal systems. Therefore, they are called as Bravais lattice. 14 Bravais lattice are possible. Let us discuss one by one. This topic is very much important for all the entrance tests. They will give you the different parameters. There are two different parameters that we have to understand. They are edge length and the angle between the edge length. So here A and B, these are the edge length along x-axis, y-axis and z-axis, A, B, C. Alpha, beta and gamma, these are all the angles between the axis x and y and z and x, that is alpha, beta and gamma. So firstly let us take the first crystal system, that is a cubic crystal system. So cubic crystal system means if all the edge lengths are equal, if A is equal to B is equal to C, all the edge lengths are equal and the angle between the edge lengths is equal to 90 degree, then such a crystal system is called as a cubic crystal system. In this cubic crystal system, there are three space lattice are possible. One is primitive, that is a simple cubic system. Next one, body centered cubic system, and face centered cubic system is possible under the cubic crystal system. Nextly, we shall move on to the tetragonal crystal system. Tetragonal system means here two edge lengths along x and y are equal. The edge length which is along the z axis is not equal, that is A is equal to B, B is not equal to C. That is A is equal to B and both are not equal to C. But the angle between all the edge lengths, that is alpha, beta and gamma, is equal to 90 degree. Under the tetragonal crystal system, there are two space lattices are possible, that is simple tetragonal system and body centered tetragonal cubic tetragonal unit cell. That is, so here there are two. The examples for the tetragonal crystal systems are the oxide of tin, oxide of stannous, oxide of titanium, zinc oxide, nickel sulfide. These are all the example for the tetragonal system. Nextly, we shall move on to orthorhombic. Very important. In this orthorhombic, so we have all the possible unit cells or all possible space lattice. Orthorhombic means all the edge lengths must not be equal. That means A should not be equal to B, B should not be equal to C. That is called as orthorhombic. But the angle between all the edge length must be equal to the 90 degree. That is alpha, beta, gamma is equal to 90 degree. Under this we have four different crystal system or space lattice, that is simple, end centered, body centered and face centered. The example for the orthorhombic, so we have these many examples, that is potassium nitrate, potassium sulfate, the lead carbonate, barium sulfate, rhombic sulfur and magnesium sulfate. These are all the example for orthorhombic crystal system. Very important. Here all the sides must not be equal but angles must be equal. So here all four possible unit cells are present, that is end center, body center, face center and simple. Nextly we shall move on to rhombohedral, or it is also called as trigonal crystal system or rhombohedral crystal system. Here all the sides are equal but the angle between the sides must not be equal to the 90 degree. It is maybe greater than 90 degree or slightly less than the 90 degree. So here only one space lattice is possible, that is simple crystal system. That is only possible. The example for the rhombohedral or trigonal system are the sodium nitrate, calcium sulfate, calcite, quartz. These are all example for the rhombohedral crystal system. Nextly we shall move on to hexagonal crystal system. Hexagonal crystal system, here the two sides which are along x and y axis are equal, but this is not equal to the third side, that is C. Here the angle between two sides, that is alpha and beta, is equal to 90 degree, but the third angle alpha, the third angle gamma is equal to 120 degree. This is a different type of crystal system where the two angles angle between two different sides is equal to 90 degree. The third angle is equal to 120 degree. There are two crystal systems. Next one is monoclinic crystal system. Here all the edge length are not equal, that is A is not equal to B is not equal to C. Alpha and gamma is equal to 90 degree, whereas the beta is equal to not equal to 90 degree. Here also there are two types of space lattice are possible, that is simple space lattice and end-centered space lattice. The example for this are the sodium sulfate dot NH2O, the sodium borate dot 14H2O, calcium sulfate dot 2H2O. These are all examples for the monoclinic crystal system. Nextly, we shall move on to triclinic system. So in triclinic, all the angles are not equal to 90 degree and all the sides are not equal to each other. Here, the only one simple unit cell is possible, that is one simple space lattice is possible. Nextly, we shall move on to the number of particles present in one unit cell. How to calculate the number of particles present in given unit cell. The number of particles present in a unit cell can be calculated by using the formula, that is Nc divided by 8, Nf divided by 2 and Nb divided by 1, because the particle which is present at the corner of the unit cell has been shared between 8 different unit cells. Therefore, the particle which is present in the unit cell, if it is divided by 8, the contribution produced to that particular unit cell is given by Nc divided by 8 divided by, similarly, Nf divided by 2. Nf divided by 2 means, here Nf means the number of particles which are present at center of the face. If the particle present at the center of the face, then this will be shared between two different unit cells. Therefore, if it is divided by 2, it will be the contribution to one unit cell. Nextly, we shall move on to Nb divided by 1. Nb divided by 1 means it is the particle which is present at the center of the unit cell is contributed to only one unit cell. Therefore, it will be divided by 1. Nextly, let us go for with some example. Let us calculate the number of particles in simple unit cell, in simple cubic system. So, by using the formula, that is Nc divided by 8 plus Nf divided by 2 and Nb divided by 1. In simple unit cell, the particle present at only at the corner. Therefore, we can write it as 8 divided by 8. At the corner, there are 8 particles at one unit cell. Therefore, it is 8 divided by 8, plus there are no particles at the center of the each faces, because it is simple crystal system. In simple crystal system, the particles will be present at only the corner. Therefore, there is no particle at the center of face and center of a unit cell also. Therefore, it is 8 divided by 8 plus 0 plus 0, that is equal to 1. Nextly, we shall move on to FCC. FCC means a face-centered cubic system. Here, the number of particles at the center of each face is equal to 8. The number of particles at the center of each face is equal to 6. You can observe here, we have 6 different faces for this unit cell. If you consider the center of the particle at the center of each faces, one particle, if we consider, that becomes 6 divided by 2, plus there is no particle at the center of the unit cell, therefore it is 0. Therefore, 8 plus 8 divided by 8 plus 6 divided by 2 plus 0, therefore that is equal to 4. Therefore, the number of particles present in FCC is 4. The number of particles present in simple unit cell is equal to 1. Now let us go through the number of particles at BCC. Number of particles in the BCC, if you consider, here from the formula we have Nc divided by 8, Nf divided by 2, Nb divided by 1. At the corner we have 8 different particles, that is 8 divided by 8. Then at the center of each faces there are no particles, therefore it is equal to 0. At the center of the unit cell we have only 1, therefore it is 8 divided by 8 plus 0 plus 1 by 1, that is equal to 2. There are 2 particles in BCC. There are 4 particles in FCC. There are 1 particle in simple cubic system.